All right, let's go ahead and continue on. Now we've talked about our project today. It's actually a good day to talk about the project because I think the material is fairly short today, which is great. So today we're going to continue our discussions on sorting. We talked about bubble sort, so we're going to continue on with selection sort and insertion sort. If I recall correctly, I asked if you were to sort a bunch of cards or whatnot, how would you go about sorting it? I think most of you all said you would take the cards, lay them out, and then find the lowest one, put it in the lowest position, find the next lowest, put in the next one. All right, and that's how a lot of people would do it. That is what selection sort is. That's how selection sort works. You look at the entire thing, you find the lowest one, and then you put that into the proper location, or largest, depending on how you want to do it. Nice thing about selection sort, it can also be applied to linked lists, because you're just looking through the whole list, find it, and then put it into the proper location. We're good to go.
It's kind of slow if it's a lot of stuff, though, isn't it?
What's that?
Wouldn't that be kind of slow, or no?
Yeah, what would be the big O of this algorithm?
It's got to go. It's got to loop through it every time.
Mm-hmm. And for every time it loops through, what does it do?
Subtracts one from the size because you're putting one in the smallest. So that'd be like n squared.
N squared. Yep.
Yeah.
Oh, what was bubble sort?
I wasn't.
Oh, you were
That was
thinking.
n log in, or
No.
just log one.
No.
Oh, then.
No, bubble sort was n squared as well.
Oh, well.
Yeah. Yeah, it was n squared in comparisons and swaps.
Yeah. I guess last class. Which one were we talking about that was log of n?
A sorting algorithm that's log of n. Wow, I'd love to see this one.
No,
All right, Jonah, you got it. Let's do it.
Log squared.
What we were saying is that on comparison-based sorting algorithms, the best you can get is n log n. We're right now at n squared, so we're still searching for an n log n algorithm.
Oh, like currently to date? People are still searching for it?
For n log, no, we got
Oh.
plenty.
I was like-
We have even n O of n sorting algorithms as well, but they're not comparison-based. They are based on something else. But anyways, let's go ahead and go back to bubble sort. Remember the quick analysis? Remember bubble sort is you start, well, let's go back here because we have pictures. You have your unsorted list, compare the top two. Oh, look, 10 is bigger, so we'll swap them. Then compare the 10 and 19. 10 is not bigger, so we keep it. Compare the 19 and the 5, compare and swap it. And then compare the 19 and 16, again, 19 is bigger, swap it. And now the 19, or the largest value, has bubbled up to where it needs to be, or bubbled down in this picture. Next, we'll again start at the top. We're comparing the 7 and the 10, don't need to swap. Compare the 10 and the 5, do need to swap. Compare the 10 and the 16, don't need to swap. So now the 16, or the second largest number, has bubbled up or bubbled down to the correct location. And then we continue it on again. 5 and 7, notice the 5 is kind of bubbling up here. And then the 7 and the 10 compare, we're okay. 10's okay, we're done. 10 bubbled. And then compare 7, and then since those are the last two, we're done. All right. That was a quick review. Total number of comparisons, n squared, because you have to go through the list. For every time you do a bubble, you have to go through the list, or about half the list. So it's half of n times n, which is essentially n squared. Number of assignments, worst case, if you have to swap every time, then again, that's n squared. All right. Everyone good? Refresh on bubble sort? All right, selection sort. Rearrange the list by selecting an element and moving it to its proper location. So you probably want to just find the smallest and then move it to the beginning. Find the next smallest, move it to the beginning. Or the end of the list, depending on which way you want to sort it. Huh. Are we not even going to talk about it? Wow, we're not even going to do a picture. All right, let's do a picture.
Better see some A+ boxes. You never really get a drawing.
Look, I mean, look, we both went to school here. And we all had to take box drawing as computer scientists, but you didn't have to get an A in box drawing.
You said, and I quote, I'm really good at box drawing. I could be better than, I'm better than anyone. We didn't have to get an A.
At least a C included.
In box,
C's get degrees.
in box. No. All right, Not going to go any further with that. Okay.
I'm not promoting seats.
All right, let's go. Give me some numbers, guys.
7. 8. 42.
10.
9,000.
Over 9,000. Looks like $1.
Is this an integer-based list, or is this,
Sure, you can make it whatever you want.
I mean, we could do like 0.5 and stuff like that. I mean, complicated.
Let's do 86.4921.
That doesn't really make that one complicated.
Yeah.
Because it's still just.
No, it's a no.
I will do 30. One of my favorite numbers. All right. So, nice little glare right up there. All right, so if we're doing selection sort, we're going to find the lowest number first, okay? So what do we have to do? Search the entire array, period, because it could be at the end. You find out it's -5. All right. So, on your first iteration, we have to search the whole array. So how many comparisons is that?
Whatever size.
Yeah. Comparisons is in, and how many swaps do we do? Because we go get to -5. I shouldn't call it swaps. Let's do assignments. Assignments. How many assignments do we do here? Because we have our new array. Oh, I'm sorry. You know what? Let's do this in place, because if I do it out of place, that's going to confuse everyone, and that's not how you should do it. All right. All right, how many swaps? So we have -5 needs to be at the beginning. But what's at the beginning right now?
30.
30. So what do we need to do?
Swap.
Swap them. So how many swaps did we have to do in this iteration?
1.
1. All right. Perfect. Okay. Now for the second iteration, how many comparisons do we do? Do we need to start at the beginning? No, we start at the next one. And then what's the lowest?
0.5.
0.5. How many comparisons do we do?
That'd be just 2, right?
N minus 1, because we still have to compare against all of them, right?
I thought you meant like up until that point.
Oh, no. We got to do all the comparisons.
Okay.
We need to swap these two numbers, right?
Yeah.
Thanks for making this really annoying one at the beginning, whoever did that. I'm going to simplify and make it 86. How many swaps did we do?
1.
All right. Third, do we need to start from the beginning?
No.
We'll start here. How many compare? So what's the lowest one? 7. All right. How many comparisons do we do? 2. How many swaps are we going to do? All right. I think we're going to 7, 86. How many? Yeah, 1 swap. I'm going to do ... because I think you've seen the pattern. What happens next?
-3.
Ignore that. What needs to go here?
8.
8. So we're swapping the 86 and the 8. I just realized there's actually N minus 1 up here, and there's N minus 2 and N minus 3, because we're just moving it on down. All right, we're here, 86. Do we need to swap it with something?
10.
10. Do we need to swap 42 with something? 30. $86?
40.
Yep. All right, so then we need to do. Okay. Great. Back in focus. There you go. All right. So, what's that?
Nothing. It's just really light on the screen.
All right, I need to get a better marker. Do you have a better marker? A red marker. Oh well.
There's one right over here.
Here, yeah. I can tell you that one if you want.
Yes, please do.
Alright.
All right, so how many comparisons did we do in total? Nice and squeaky. Oh, that is better. How many comparisons do we do?
Is it the size of the list?
Well, you gotta do, yeah, size of the list, which is times, yeah, times something which equals O of n squared. Right? How about swaps? How many swaps did we do? 1, 1, 1. How many times do we do a swap of 1?
N times?
So, O of n. Okay. Let me make that 2 a little better. All right. So the swaps was O of n. That's good. And the comparison's n squared. So is it better or worse than bubble sort?
Same. Well, slightly better.
The comparisons are the same. How about the swaps?
Better.
Better, right, because a bubble sort could swap every time and be n squared. This time you're basically guaranteeing n times that you swap. Go look at the slides real quick. Let's see, swap just 3 assignments and execute n minus 1 time, so it's O of n. And then key comparisons, multiply that all out, because you have for a list of length k minus 1 key comparisons, executed n minus 1 times. So you multiply that all out. By the way, are you all familiar with this conversion right here? This equals that. Did y'all learn that one yet? I have one person saying yes, and the rest of y'all kind of confused? So in discrete structures, you took discrete. Or discrete, what's it called? Discrete?
It's called discrete math.
Discrete math. And you did the all-important computer science formula of I equals 0 to n of I, summation, you know, 1 plus 2 plus 3 all the way up to n. What'd that one equal?
Except 1. N times n plus 1 over 2.
All right. Remember, that's the all-important computer science formula. There's also one for I squared, but this is the one we care about. Okay? So all they did to convert from there is they said, okay, I is going to equal, well, it's I minus 1. You're losing one term, so that's why it's n minus 1 on this regards. So they still use the same formula. Because in actuality, they're doing this. Whoop. So you're not doing the last n. So hopefully you can see if you subtract an n, it's just, yeah, minus 1. Okay. All right, we're good there?
Yes.
Excellent. Let's go and stop.